Hello everyone, it's glad to be here, introducing Pointly-supervised Scene Parsing with uncertainty mixture. In this research, we have 4 contributions: a discovery, a pipeline, a model, and an evaluation. Firstly, the discovery. We identify the existence of previously unknown statistical phenomena, which we call uncertainty mixture. Secondly, based upon this discovery, we propose a principled pipeline, a framework, to harvest pseudo labels for pointly-supervised scene parsing, notably, without the need of threshold tuning. Then, within this framework, we contribute a new mixture model. It is a gamma mixture model with regularization. And at last, we achieve state-of-the-art results on 2 challenging benchmarks. So 4 contributions, and let's start with the discovery. As we know, finite mixture models is a powerful tool in computer vision applications. The most famous case should be modeling pixel intensity in surveillance camera streams, background subtraction. And another case is modeling normals in Manhattan indoor scenes. There are just 2 examples among many other applications of finite mixture models. However, in the deep learning era, it seems that neither neural network weights nor features naturally emerge as mixture models. So is this powerful tool still useful? And our answer is uncertainty mixture. Okay, the discovery. We identify the fact that uncertainty measures, they emerge as gamma mixtures. So here comes the motivation, the problem setting. In pointly-supervised scene parsing, only these red dots have ground truth labels. And we can train a model using these point supervisions, and we call this model the first round model. And then we fit the whole training set into the first round model to get pseudo labels and uncertainty measures. We can see that pseudo labels are noisy. Some of them are correct and the others are wrong. And our goal is to look for good, high quality and correct pseudo labels so that they can be used for training. And I believe after seeing these uncertainty maps, everyone would agree that harvesting pseudo labels with low uncertainty is a promising proposal. However, a problem must be resolved. How do we define low uncertainty? Using threshold is a trivial solution, but tuning thresholds is too expensive for deep neural networks. So we ask the question, is there a principled method to automatically find the optimal threshold for harvesting pseudo labels? And the answer is uncertainty mixture. Please look at these histograms. They are category-wise uncertainty measure histograms for pseudo labels. Please note that the AD data set has 150 categories, and the Pascal context data set has 60 categories. It is quite surprising that for all these categories, the uncertainty measure histogram, they all emerge as a 2-peak distribution. So after seeing these histograms, I believe the first word that jumps into everyone's head is finite mixture models. And specifically, we use gamma mixture models to model these histograms. And here comes 3 reasons why we use gamma mixture. instead of Gaussian mixture. Let's denote the low uncertainty component LUC and the high uncertainty component HUC. First reason. Uncertainty measures, they are actually variance. So they are always positive. The support of gamma function is the real axis, the positive real axis, so a great match. Secondly, we can see that LUC is always picked near zero because they are low uncertainty components. Okay, so it's obvious that it's problematic to model LUC with a gamma function. Thirdly, one may argue that HUC looks quite Gaussian. This is fine, okay, because intrinsic property of gamma distribution is that when the alpha parameter grows, a gamma distribution approaches a Gaussian distribution. So here comes the pipeline, harvesting LUC labels and fine-tune the net. The first step, train the first round model using point supervision, as just mentioned. Then we can get pseudo labels and uncertainty measures on the training set, as just mentioned. Okay. Thirdly, we need to use EM algorithms to estimate the parameters for LUC and HUC on a category-wise basis. Then we just harvest all the pseudo labels that belong to LUC. Finally, we fine-tune the first round model using harvested pseudo labels. So this is a pipeline, and it is worth noting that during the procedure of harvesting pseudo labels, there is no manual thresholding. Okay. The third contribution is a regularized gamma mixture model. Okay. Please look at the left top figure. It's a histogram for unlabeled points, but predicted as waterfall in the pseudo label outputs. And then look at the left bottom figure. It's uncertainty measure histogram for all waterfall supervision points. So the idea is to assume all labeled points always belong to LUC, and this leads to a regularization term. Actually, this is a new model. According to our review, no one has studied this model before, so we provide a detailed analytical exposition for this model, including a convergence guarantee proof. Okay, please check for details, please check the paper. At last, the results. Okay. On the left, we show Pointly-supervised scene parsing results, and on the right, the transductive inference results. We have checked different backbones of different layers. We can see that after the regularization term, the performance always goes up. And the reason is revealed on the right. The regularization term leads to higher precision and a little bit lower recall. More insights. Here, the relationship between segment area, the amount of supervision points, and the precision recall. The relationship between distance transform and uncertainty measures. However, according to these results, we have to say that drawing supervision points near boundaries is a promising idea, but not ready in our framework. And our research is still ongoing. We are checking other uncertainty measures. So this is our presentation. As take-home messages, we have 4 contributions. a discovery, a pipeline inspired by the discovery, and a new mathematical model within the pipeline, and an evaluation. Thank you.